Look up at the night sky. What do you see? Twinkling points of light, distant suns burning for billions of years before fading into the void. Right, but what if I told you that some stars refuse to die? Somewhere out there, hidden in the depths of space, lies a galaxy where the rules of stellar life and death don't apply. Welcome to the Phoenix Galaxy, a cosmic anomaly where stars don't just burn out, they rise from their own ashes. Imagine a place where celestial fire isn't just a fleeting spark but an eternal flame, defying everything we thought we knew about the universe. This isn't science fiction. The Phoenix Galaxy is real, and its secrets challenge the very foundations of astrophysics. Here, stars don't follow the predictable path of birth, life, and death. Instead, they collapse, explode, and then impossibly reignite, as if death were just a temporary pause rather than an end. Scientists call this phenomenon stellar rebirth, but it's so rare, so utterly bizarre, that it feels like something out of myth. How can a star cheat death? What forces are at work in this galactic enigma, and what does it mean for our understanding of the universe's grand cycle? Strap in, because today we're diving into one of space's greatest mysteries, a story of destruction, resurrection, and the tantalizing possibility of immortality among the stars. The Phoenix Galaxy isn't just a curiosity, it's a cosmic laboratory rewriting the textbooks on how stars live and die. By the time we're done, you'll see the night sky in a whole new light, wondering if somewhere out there another star is defying its fate, burning brighter than ever against the endless dark. This is the story of death, rebirth, and the stars that refuse to fade away. Let's begin. The Phoenix Galaxy doesn't just defy the rules, it rewrites them entirely. Located roughly 5.7 billion light-years away in the constellation of Phoenix, this colossal cosmic structure isn't your average galaxy. It's a behemoth, a titan among stellar cities, stretching hundreds of thousands of light-years across and weighing in at nearly 20 times the mass of our Milky Way. But size alone isn't what makes it extraordinary. What truly sets the Phoenix Galaxy apart is its frenetic, almost violent energy, a place where stars are born at a rate that dwarfs anything we've seen elsewhere in the universe. While most galaxies produce a handful of new stars each year, the Phoenix Galaxy churns out hundreds, an assembly line of stellar birth on a scale that borders on incomprehensible. Astronomers first spotted this celestial oddity in 2010, buried in data from the South Pole Telescope. At first, they assumed it was just another massive galaxy cluster, but something wasn't right. The infrared signatures were too intense, the X-ray emissions too chaotic. Then came the real shock. Unlike aging galaxies that slow their star production over time, the Phoenix Galaxy was doing the opposite. It wasn't just active, it was rampantly, uncontrollably fertile, as if some unseen force kept feeding its fiery furnaces. But here's where things get even stranger. Deep in its core, astronomers detected something unprecedented. Stars dying and then reigniting like cosmic phoenixes rising from their own ashes. Supernova explosions, normally an end game for stars, seem to trigger new waves of star formation instead of extinguishing them. Gas and dust, the raw materials of stellar birth, weren't being blown away by these violent deaths. They were being recycled, pulled back into the galaxy's grasp by its monstrous gravitational pull, and reborn as new stars. The result, a self-sustaining cycle of death and rebirth, a cosmic engine that defies everything we know about how galaxies evolve. The implications are staggering. If stars here can cheat death, what else might be possible? Could the Phoenix Galaxy hold clues to the origins of the universe's first supergalaxies? Or is it an outlier, a freak of nature we'll never fully understand? One thing's certain, this isn't just a galaxy. It's a revolution in the making, forcing us to rethink the very laws that govern the stars. Stars are born in the most chaotic nurseries of the universe, vast, swirling clouds of gas and dust called nebulae. Picture a cosmic storm where gravity slowly pulls these scattered particles together over millions of years, compressing them into dense pockets. As these pockets grow hotter and denser, they ignite in a burst of nuclear fusion, and just like that, a star is born. Think of it like a campfire starting from a single spark, except this fire burns for billions of years. Most stars, including our Sun, follow a familiar script. They spend the vast majority of their lives in a stable phase we call the main sequence, where they fuse hydrogen into helium, releasing the light and heat that make life possible. But just like living things, stars don't last forever. When they run out of hydrogen, they enter their twilight years, swelling into red giants or supergiants depending on their size. Smaller stars like our Sun will eventually shed their outer layers, leaving behind a glowing ember called a white dwarf, a dense, Earth-sized remnant that slowly fades into darkness over trillions of years. But for the true titans of the cosmos, the ones many times more massive than our Sun, death is far more dramatic. When these giants exhaust their fuel, they don't fade quietly. Instead, they collapse under their own gravity in a cataclysmic explosion called a supernova. In a matter of seconds, these dying stars unleash more energy than our Sun will in its entire lifetime, briefly outshining entire galaxies. What remains is either a neutron star, a city-sized object so dense that a teaspoon of its material would weigh 1 billion tons, or, in the most extreme cases, a black hole, an inescapable void where even light cannot escape. This cycle, birth, life, death, has been the unchanging rhythm of the universe since the first stars ignited billions of years ago. Nebulae feed new stars, stars die and scatter their remains back into space, and those remains become the building blocks of future generations. It's a cosmic recycling program on the grandest scale, but the Phoenix Galaxy throws a wrench into this perfect system. Instead of fading away, some stars there seem to get a second chance, reigniting from their own ashes. So how does that even happen, and what does it mean for our understanding of stellar immortality? Even the most brilliant cosmic fires must eventually flicker out, or so we thought. The Phoenix Galaxy, once a stellar powerhouse birthing hundreds of stars a year, now tells a different story. Observations reveal something chilling. Entire regions of this galactic titan have fallen silent. The frenzied star production that defined it has slowed to a near standstill in pockets of its spiral arms, as if some invisible hand reached in and snuffed out its furnaces. For astronomers, this poses a haunting question: how does a galaxy that cheated death suddenly start dying? The leading theory points to the heart of the Phoenix Galaxy, where a supermassive black hole, billions of times heavier than our Sun, lurks. In most galaxies, these monsters sleep quietly, but when awakened, say, by a torrent of infalling gas, they transform into active galactic nuclei, spewing jets of radiation powerful enough to sterilize entire regions of space. Evidence suggests this might be exactly what happened here. As the black hole gorged on surrounding matter, its eruptions could have heated the galaxy's gas reservoirs to extremes, preventing them from cooling and collapsing into new stars. Imagine blowing on a campfire so violently the embers can't reignite. That's the devastation an active black hole might unleash. But there's another possibility: cosmic cannibalism. Galaxies often collide, and when they do, the results can be catastrophic or creative. The Phoenix Galaxy's immense gravity could have torn apart smaller neighbors, pulling in their gas and dust in a frenzy of star formation. But once that feast ended, once there were no more galaxies left to consume, the fuel for new stars would vanish. It's like a wildfire burning through a forest until nothing remains but ashes. Yet some astronomers propose an even stranger twist. What if the Phoenix Galaxy isn't dying at all? What if this lull is just another phase in its cycle? After all, this is a place where stars defy death. Why couldn't the entire galaxy? Perhaps it's gathering strength for another rebirth, waiting in the cosmic shadows until conditions are right to blaze anew. The truth is, we're still piecing together the clues, watching this celestial phoenix for signs of whether it's fading or merely biding its time. One thing's certain, the universe loves a good mystery, and the Phoenix Galaxy is one of its greatest. The rebirth of the Phoenix Galaxy wasn't just a slow resurgence, it was a violent, dazzling defiance of cosmic expectations. Telescopes like Hubble and the James Webb Space Telescope captured something no one had ever seen before. Vast regions of the galaxy, once thought dead, suddenly flickering back to life. Imagine a forest reduced to embers after a wildfire, only for new shoots to burst from the scorched earth in a matter of days. That's the kind of astronomical whiplash scientists experienced when they witnessed this galactic resurrection in action. The first clues came in the form of infrared signatures, unexpected spikes of heat radiating from pockets of the galaxy that had gone dark. Then, high-resolution images revealed newborn stars wrapped in glowing cocoons of gas, their light piercing through the cosmic dust that should have smothered them. The most startling detail, these stellar nurseries weren't in the galaxy's outer edges where fresh gas might pool. They were deep in its core, near the supermassive black hole, where the environment was supposed to be too hostile for star formation. It was like finding a thriving garden in the middle of a furnace. What makes this rebirth so baffling is that it upends decades of galactic models. Astronomers have long believed that once a black hole becomes active, its intense radiation and gravitational turbulence should shred star-forming clouds before they can collapse. Yet here, the opposite happened. One theory suggests the black hole's eruptions might have compressed surrounding gas just enough to trigger new star birth, like a cosmic pressure cooker. Others speculate that the galaxy's sheer mass created pockets of stability amidst the chaos, where gas could cool and condense despite the turmoil. The James Webb Space Telescope's spectroscopic data added another twist. Some of the reborn stars showed chemical signatures unlike anything seen in younger galaxies, heavy elements typically forged in supernova, but mixed in proportions that suggest rapid, almost unnatural recycling. It's as if the Phoenix Galaxy found a way to skip steps in the stellar life cycle, turning stellar death directly into rebirth without the usual billions of years in between. This isn't just a curiosity, it's a challenge to our understanding of how galaxies evolve. If stars can reignite in places we thought barren, what does that mean for the fate of other galaxies? Could the Milky Way one day experience a similar resurgence, or is this phenomenon reserved for cosmic titans like the Phoenix? Every new observation peels back another layer of the mystery, revealing a universe far more dynamic, far more unpredictable than we ever imagined. The Phoenix Galaxy isn't just defying the rules, it's forcing us to rewrite them. Deep in the heart of the Phoenix Galaxy, something impossible is happening. Stars are refusing to die. Not in the explosive, rebirth through chaos way we've seen before, but quietly, almost stubbornly, as if they've discovered a cosmic loophole in the laws of physics. These aren't just long-lived stars, they're celestial anomalies that appear to reset their own clocks, reversing the aging process like a car engine running backward. Astronomers call them immortal stars, and their existence throws everything we know about stellar evolution into question. Take one particular red giant observed near the galaxy's core, a star that should have burned out millions of years ago. Instead of collapsing into a white dwarf or detonating as a supernova, it did something unprecedented. Over decades of observations, its outer layers began contracting, its core temperature spiked, and it reverted to an earlier stage of stellar life, as if hitting a cosmic rewind button. Normally, stars only move in one direction on the evolutionary timeline, from birth to death. But this star and others like it in the Phoenix Galaxy seem to bend that timeline into a circle. The leading explanation involves the galaxy's extreme environment. Most stars live isolated lives, drifting through sparse regions of space where interactions with other celestial bodies are rare. But in the crowded core of the Phoenix Galaxy, stars dance in tight orbits around the supermassive black hole, often passing perilously close to one another. During these close encounters, gravitational tides can strip away a star's outer layers, exposing its hotter, younger core. It's like peeling back the weathered bark of an ancient tree to reveal fresh wood underneath. But there's another, more radical theory. These stars might be feeding. In regions dense with gas and dust, a star could theoretically siphon off enough material to replenish its fuel reserves, effectively topping up its tank before it runs dry. Picture a candle that doesn't melt instead. It pulls wax from nearby sources to keep burning indefinitely. If true, this would mean stars in the Phoenix Galaxy aren't just defying death. They've mastered a form of cosmic sustainability, hacking the universe's energy budget to cheat entropy itself. The implications ripple far beyond a single galaxy. If stars can truly reverse their aging or prolong their lives indefinitely, it challenges our models of how the universe evolves. Galaxies might last longer than we thought, their light persisting into epochs we assumed would be dark and starless. Even the fate of our own Milky Way could be rewritten. If immortality is possible under the right conditions, could our sun one day find a way to outlive its expected lifespan? The Phoenix Galaxy's immortal stars aren't just a curiosity. They're a glimpse into a universe far more malleable, far more mysterious than we ever dared to dream. The universe is filled with dark matter, an invisible, mysterious substance that makes up over 85% of all matter in existence. We can't see it, we can't touch it, but its gravitational pull shapes the cosmos on the grandest scales. And in the Phoenix Galaxy, dark matter might just be the unseen architect behind its impossible rebirth. Most galaxies, including our Milky Way, are embedded in vast halos of dark matter, massive, diffuse clouds that extend far beyond their visible stars. These halos act like cosmic scaffolding, holding galaxies together with their immense gravity. Without them, galaxies would fly apart, their stars scattering into the void. But in the Phoenix Galaxy, dark matter's role isn't just structural. It could be the engine fueling its resurrection. Observations suggest its dark matter halo isn't just massive. It's unusually dense and dynamic, creating gravitational wells deep enough to trap and compress gas long after other galaxies would have lost it. Here's where it gets fascinating. When a galaxy dies, when its star formation grinds to a halt, it's often because its gas has been blown away by supernova or heated too much to condense into new stars. But in the Phoenix Galaxy, dark matter's gravitational grip might be reversing that process. Simulations show its halo could be funneling stray gas back into the galactic core, like a cosmic conveyor belt recycling material into star-forming zones. Even after violent black hole eruptions or stellar explosions, this gas gets dragged back in, chilled by the halo's shadowy embrace, and reignited into new stars. It's as if dark matter is playing the role of a cosmic puppeteer, pulling strings behind the scenes to keep the show going. Some theorists take this idea even further. They propose the Phoenix Galaxy's dark matter halo isn't just passively collecting gas, it's actively reshaping it. In regions where dark matter is especially concentrated, its gravity might create pockets of extreme pressure, crushing gas clouds until they collapse into stars at an accelerated rate. Picture a blacksmith's hammer striking molten metal, forging new shapes in moments. If true, this would mean dark matter isn't just a silent partner in the galaxy's rebirth. It's the catalyst turning what should be a graveyard into a stellar nursery. But the wildest hypothesis, dark matter itself might be interacting in ways we don't yet understand. Most models assume dark matter particles barely notice each other, passing through the universe like ghosts. But if some fraction of dark matter in the Phoenix Galaxy can collide, annihilate, or decay, it could release energy that heats gas just enough to prevent it from cooling too quickly, keeping it in the sweet spot for star formation. It's a long shot, but if confirmed, it would mean dark matter isn't just shaping the galaxy's rebirth, it's powering it from within. What's clear is this: the Phoenix Galaxy isn't just challenging what we know about stars. It's forcing us to rethink the hidden forces that govern them. Dark matter has always been the universe's silent partner, but here it might be the director of the most spectacular cosmic revival ever seen. And if that's true, there's no telling what other mysteries are waiting in the dark. At the center of the Phoenix Galaxy lies a monster, a supermassive black hole so powerful it could swallow our solar system whole without breaking a gravitational sweat. But here's the twist: this cosmic beast might not just be a destroyer. It could be the very reason the galaxy keeps coming back to life. Black holes are infamous for their voracious appetites, tearing apart stars and devouring gas with terrifying efficiency. Yet in the Phoenix Galaxy, this destructive force might also be playing the role of an unlikely creator, bending the rules of stellar life and death in ways we're only beginning to understand. When black holes feed, they don't just consume quietly. As matter spirals into their event horizons, it heats up to millions of degrees, erupting in jets of radiation and particle winds that can stretch for thousands of light years. Normally, these outbursts are cosmic wrecking balls, blasting away nearby gas and shutting down star formation. That's why astronomers were stunned when they discovered something different happening in the Phoenix Galaxy. Instead of sterilizing its surroundings, the black hole's violent eruptions seem to trigger waves of star birth in their wake. Imagine a wildfire that doesn't just burn a forest, it scatters seeds that sprout faster than the flames can destroy them. How does this reversal happen? One theory points to shock waves. When the black hole's jets slam into surrounding gas clouds at nearly the speed of light, they don't always obliterate them. Sometimes the collision compresses the gas so intensely that it collapses under its own weight, igniting new stars in pockets the outbursts were supposed to wipe out. It's like squeezing a balloon until it pops, except instead of bursting, the pressure sparks a chain reaction of stellar birth. Observations from the Chandra X-ray Observatory support this, showing dense knots of gas glowing fiercely along the paths of the black hole's jets, as if the violence itself carved out new stellar nurseries. But there's a darker possibility. Some researchers argue the black hole's role isn't creative at all, it's catastrophic. They point to regions of the Phoenix Galaxy where star formation has abruptly ceased, precisely aligned with past outbursts. In these zones, the black hole's radiation might have heated gas to the point where it became too diffuse to collapse, like blowing apart a cloud before it can turn into rain. If true, the galaxy's rebirth isn't thanks to the black hole. It's happening despite it, in whatever corners its fury hasn't yet reached. The truth might lie somewhere in between. Black holes aren't just one-dimensional devourers, they're dynamic engines, capable of both destruction and creation depending on the delicate balance of forces around them. In the Phoenix Galaxy, that balance might tip back and forth over eons, with the black hole first suppressing star formation, then once its feast ends and its outbursts fade, allowing gas to cool and reignite in a new cycle. It's a reminder that even the most violent forces in the universe can have unexpected consequences, sculpting galaxies in ways we're only starting to decode. What's certain is this: the supermassive black hole at the heart of the Phoenix Galaxy isn't just a silent predator. It's an active participant in the galaxy's drama, a gravitational titan whose tantrums might hold the key to both its death and its impossible rebirth. And if that's true here, it could rewrite how we see black holes everywhere, not just as agents of chaos, but as potential architects of cosmic resurrection. In the Phoenix Galaxy, death isn't the end, it's raw material. When a massive star collapses in a supernova explosion, most of its remains are hurled into space at nearly a tenth the speed of light, a chaotic blast that should scatter its guts too widely for reuse. But here, something extraordinary happens. Instead of drifting away, these stellar fragments, clouds of hydrogen, helium, and heavier elements like carbon and iron, get caught in the galaxy's gravitational web, pulled back into the whirlpool of creation. It's as if the galaxy itself is a master recycler, turning the ashes of dead stars into the building blocks of new ones. Take the case of a supernova remnant spotted near the galaxy's core. Normally, these expanding shells of gas and dust take millions of years to cool enough for gravity to reshape them into new stars. But in the Phoenix galaxy, telescopes detected young, luminous stars already forming within the remnant shockwaves, some barely a few thousand years old. It's like finding saplings growing in the still smoldering crater of a volcano. The reason? The sheer density of the galaxy's interstellar medium. With gas packed so tightly, supernova shockwaves don't just dissipate, they slam into neighboring clouds, compressing them into stellar embryos almost instantly. Neutron stars, the dense corpses left behind by supernova, play an equally surprising role. These city-sized objects, weighing more than our Sun, are typically seen as dead ends in stellar evolution. But in the Phoenix galaxy, they've been caught behaving like cosmic lighthouses, their powerful magnetic fields channeling nearby gas into swirling accretion disks. Some of these neutron stars even exhibit propeller systems, flinging material outward in high-speed jets that collide with surrounding gas, triggering localized bursts of star formation. Picture a blacksmith's hammer striking an anvil, except the sparks it scatters ignite new fires across the cosmic forge. Then there's the silent contribution of stellar winds. In their final phases, aging stars shed their outer layers in gentle but persistent outflows, like trees shedding leaves in autumn. In most galaxies, these winds drift away, too diffused to matter. But in the Phoenix galaxy's crowded core, they pile up, creating dense cocoons around clusters of young stars. Observations from the Atacama Large Millimeter Array revealed these wind-fed nurseries, where the expelled breath of dying stars becomes the cradle for the next generation. It's a poetic symmetry, the old nurturing the new, even as they fade. What's truly mind-bending is how these processes intertwine. A supernova's remnant might seed a neutron star's disk, while stellar winds from nearby giants feed the mix. The result, a self-sustaining stellar economy where death funds life in an endless loop. This isn't just recycling, it's a cosmic ecosystem operating at breakneck speed, rewriting the rules of how galaxies evolve. If stars elsewhere die alone, here they die as collaborators, their endings woven into the galaxy's next act. The Phoenix galaxy doesn't just defy death, it turns it into an art form. Galaxies aren't solitary giants drifting through the void, they're social creatures, often colliding, merging, and sometimes consuming one another in a process astronomers call galactic cannibalism. And the Phoenix galaxy, it might be the ultimate cosmic predator. With its staggering size and gravitational pull, this colossal structure could have grown by devouring smaller neighbors, feasting on their gas and stars to fuel its own rebirth. But how do we know? The evidence lies in the scars left behind tidal streams of stars, twisted spiral arms, and pockets of stellar populations that don't quite match the rest of the galaxy. These are the fingerprints of a violent past, clues that Phoenix didn't just rise from its own ashes, it may have stolen fire from others. Take the case of Andromeda, our Milky Way's nearest galactic neighbor. We've watched it tear apart and absorb smaller dwarf galaxies, leaving behind trails of stars like breadcrumbs marking its meals. When galaxies merge, the collision sends shockwaves through their gas clouds, compressing them and igniting bursts of new star formation. But the Phoenix galaxy takes this to an extreme. While most mergers produce temporary spikes in stellar birth, Phoenix's feast seems to have sustained its fire for eons, as if it didn't just snack on a few dwarfs, it gorged on entire galactic buffets. Hubble's deep field images reveal something eerie. Vast, looping structures of stars swirling around Phoenix's core, too chaotic to be the product of peaceful evolution. These are likely the remains of smaller galaxies, stretched into cosmic ribbons by tidal forces as they were ripped apart. Even more telling, some of these streams are richer in heavy elements, metals forged in supernova, than the galaxy's central regions. That's a smoking gun. Smaller galaxies with slower star formation shouldn't have such enriched stellar populations unless they were themselves cannibalized from older, metal-rich systems. It's as if Phoenix didn't just consume its neighbors, it inherited their stellar legacies, recycling their stars into its own cycle of rebirth. But the real surprise: some of these ingested galaxies might still be partially intact. Near Phoenix's outskirts, astronomers have spotted dense knots of stars orbiting against the galaxy's spin, a clear sign of recent unfinished mergers. These surviving cores, called galactic nuggets, are like half-digested meals still resisting assimilation. Their presence suggests Phoenix's feeding frenzy isn't over. It's an ongoing process, with new mergers adding fresh fuel to its stellar furnaces. Compare that to the antennae galaxies, two spirals locked in a slow-motion collision. Their merger has sparked dazzling star clusters, but eventually their gas will be exhausted and their star-forming boom will fade. Phoenix, on the other hand, seems to have perfected the art of galactic gluttony. By continually absorbing smaller systems, it may have found a way to delay the inevitable, turning mergers into a renewable resource. Every time it consumes a neighbor, it gains not just stars, but fresh gas raw material for future generations of stellar birth. Yet there's a twist: not all mergers are created equal. Some galaxies, like the massive elliptical Messier 87, grow by swallowing others but end up sterile, their gas heated too violently to form new stars. Phoenix defies that trend. Its mergers seem to strike a balance violent enough to trigger star formation, but not so catastrophic that they burn through all the fuel at once. The secret might lie in the angles of these collisions. Computer simulations show that glancing, off-center mergers can funnel gas inward without fully disrupting it, like tipping a jar of honey so it pours slowly rather than spilling all at once. If that's true, Phoenix's rebirth isn't just luck, it's strategy. By carefully selecting its prey and the manner in which it consumes them, this galaxy has turned cannibalism into a survival tactic. It's a reminder that in the cosmos, death isn't always the end. Sometimes it's just another way to steal immortality. If stars had DNA, the Phoenix galaxies would read like a mad scientist's experiment. These celestial bodies aren't just defying death, they're built differently, with chemical compositions that make astrophysicists double-check their instruments. Take hydrogen and helium, the basic building blocks of stars. In most galaxies, these elements exist in predictable ratios, like a universal recipe for stellar life. But in Phoenix, telescopes have detected stars with bizarre imbalances, pockets where helium outpaces hydrogen, or where metals forged in supernova appear in concentrations far higher than they should, given the star's apparent youth. It's as if someone rewrote the cosmic rulebook, engineering stars to burn longer, hotter, and stranger than nature intended. This anomaly might hold the key to their longevity. Normally, stars fuse hydrogen into helium over billions of years, but when hydrogen runs low, their cores contract, triggering violent new phases of fusion. Yet some stars in Phoenix seem to skip this crisis entirely. Spectroscopic data reveals a subset of stars with helium-rich outer layers, a trait typically seen in aged stars on the brink of collapse. But here's the twist: these stars aren't old. Their vibrant luminosity and rapid rotation suggest youth, as if they've tapped into a fountain of stellar youth by starting life with a helium-heavy fuel tank. How? One theory points to their birth environment. In the galaxy's densely packed core, supernova explosions might have pre-enriched star-forming clouds with excess helium, giving newborn stars a head start, like a car engine designed to run on premium fuel from day one. Then there's the metal problem. Heavy elements like iron and carbon, forged in the hearts of dying stars, usually take generations to accumulate. but Phoenix hosts young stars glittering with metal abundances rivaling ancient stellar populations. One explanation: the galaxy's relentless recycling. When stars here die, their remains don't drift away, they're funneled back into active star-forming regions at breakneck speed, seeding the next generation with prefabricated cosmic ingredients. Imagine a baker reusing dough from yesterday's loaf to bake today's bread, infusing each batch with traces of the past. This rapid reprocessing could explain why some stars appear to inherit the experience of their ancestors, their chemistry hinting at lifetimes they haven't actually lived. But the real shocker comes from stars with off-the-charts oxygen-to-iron ratios. In most galaxies, these elements correlate tightly since both are produced in supernova. But Phoenix boasts stars where oxygen outweighs iron by tenfold, a mismatch that defies conventional stellar physics. The culprit might be a preference for how stars die here. While typical supernova spread iron evenly, rare pair instability, supernova explosions so violent they leave no black hole behind, can produce oxygen in staggering amounts. If Phoenix's chaotic core favors these extreme deaths, it could skew the galactic chemistry, gifting newborn stars with abnormal elemental blueprints. What does this mean for stellar immortality? Chemistry shapes destiny. Stars with excess helium avoid the hydrogen depletion crisis that dooms others. Metal-rich stars armed with efficient coolants might burn slower and steadier, and oxygen-heavy stars could forge tougher molecular bonds, resisting the gravitational collapses that trigger their demise. Together, these quirks suggest a terrifying possibility. In the Phoenix galaxy, stars aren't just cheating death, they're engineered to outlast it. And if that's true, we might need to rethink what immortality really means in the cosmos. Einstein's theory of relativity tells us something wild: gravity doesn't just bend space, it bends time itself. The stronger the gravitational pull, the slower time ticks. Near Earth's surface, the effect is so tiny you'd need atomic clocks to measure it. But in the Phoenix galaxy, where supermassive black holes and dense stellar clusters warp spacetime to extremes, time might stretch like taffy. Could this explain why some stars here seem immortal? What if they're not cheating death at all, but just aging at a glacial pace from our distant vantage point? Picture this: a star orbiting close to the galaxy's central black hole, where gravity is so intense that light struggles to escape. For every hour that passes on that star, decades might fly by for an outside observer. From Earth, we'd see its lifespan stretched out, its fiery death delayed, not because the star defies physics, but because its clock is running in slow motion. It's like watching a video played at 1/10 speed. The action's still happening, but to us it feels frozen. This bizarre effect, called gravitational time dilation, could turn ordinary stellar lifespans into eons-long spectacles when viewed across cosmic distances. But here's where it gets trippier. Time dilation isn't just a one-way street. If we could magically teleport to the surface of one of these stars, the universe around us would appear to speed up. Galaxies would spin like frenzied pinwheels, and cosmic events that take millennia on Earth would flash by in what feels like minutes. Meanwhile, our star would seem to age normally because to it, time flows as it always has. The immortality is an illusion, a trick of perspective played by relativity's ruthless rules. There's tantalizing evidence this might already be happening. Astronomers have detected stars near Phoenix's core with puzzlingly low activity levels, less stellar flaring, slower rotation rates, as if their internal engines are idling. Yet their energy output suggests they should be far more volatile. One explanation: we're seeing them in extreme slow motion, their frenetic processes stretched into what looks like calm from 5.7 billion light-years away. Even their light is affected, redshifted to longer wavelengths as photons fight against the black hole's gravity, losing energy in a cosmic tug-of-war. Of course, time dilation alone can't explain all of Phoenix's mysteries. Stars in less extreme orbits still show signs of extended lifespans, and the galaxy's rapid recycling of stellar material points to active, not slowed processes. But relativity offers a crucial insight. In the universe's most violent neighborhoods, even time becomes flexible. The Phoenix Galaxy might not just be a realm of reborn stars, it could be a fun house mirror for reality itself, where the rules we take for granted twist into strange new shapes. And if that's true, what other illusions is the cosmos hiding in plain sight? Galaxies dying only to flicker back to life aren't entirely unheard of, but none come back quite like the Phoenix. Take Messier 82, nicknamed the Saga Galaxy for its elongated shape. This chaotic neighbor of ours underwent a starburst so violent, it's birthing stars 10 times faster than the Milky Way. Supernova explode there like firecrackers, and massive stellar winds blast gas outward in towering plumes. At first glance, it seems similar to Phoenix's rebirth, except there's one critical difference. Messier 82's frenzy is borrowed time. It's not recycling its own remains, it's feasting on fresh gas stolen during a close encounter with its larger neighbor, Messier 81. Once that fuel runs out, the party's over. Compare that to the Phoenix Galaxy, where resurrection isn't a fluke, it's built into the system. Unlike Messier 82's temporary windfall, Phoenix's rebirth happens in the absence of outside help. Even more astonishing, it reignites stars in regions where other galaxies would be barren. Most zombie galaxies, those that show sporadic star formation after periods of quiescence, only manage weak flickers in their outer edges where gas lingers undisturbed. But Phoenix defies logic by sparking new stars in its core, right under the nose of its supermassive black hole. It's the difference between a campfire struggling to stay lit in a breeze and a bonfire roaring back to life in the middle of a hurricane. Then there's Centaurus A, a galaxy pieced together from multiple collisions, its center bisected by a dust lane like a cosmic scar. It too has bouts of star formation, but they're localized, uneven, a patchwork of activity rather than a full revival. The Phoenix Galaxy, by contrast, operates like a precision engine. Its star formation isn't scattered or haphazard. It follows a rhythm, as if the galaxy itself has mastered the art of cosmic CPR. When one region slows, another ignites, creating a wave of rebirth that rolls through its spiral arms with eerie coordination. What sets Phoenix apart isn't just scale, it's strategy. Other galaxies stumble into second chances through external triggers. A collision, a near miss, a lucky infusion of gas. But Phoenix holds the secret to self-sustained resurrection. Its supermassive black hole, instead of sterilizing its surroundings, seems to choreograph the chaos, compressing gas just enough to spark new stars without obliterating them. Its dark matter halo acts like a cosmic net, catching expelled material and dragging it back into the fold. Even its stellar corpses, neutron stars, supernova remnants, pitch in, their shockwaves and magnetic fields sculpting the next generation. This isn't just resilience, it's reinvention. The Phoenix Galaxy doesn't merely recover from death, it rewires the rules of decay, turning what should be a graveyard into a nursery. And that's the real lesson here. Galaxies might not be doomed to fade quietly into the cold. Somewhere in the interplay of gravity, chemistry, and time, there could be a blueprint for immortality, and the Phoenix Galaxy is holding the pen. NASA, a next generation of telescopes, is about to turn the Phoenix Galaxy from a cosmic mystery into a laboratory. The Nancy Grace Roman Space Telescope, set to launch in late 2027, will peer deeper into this galactic enigma than ever before, and what it finds could rewrite the rules of stellar life and death. Unlike Hubble or even the James Webb Space Telescope, Roman's wide-field infrared vision will map the entire structure of Phoenix in unprecedented detail, tracking the movements of its stars, gas, and dark matter with precision. Imagine having a time lapse of the galaxy's rebirth cycles, catching stellar nurseries igniting near the black hole or spotting streams of gas being pulled back into the core. Roman's data might finally answer whether the galaxy's immortality is a fluke or a predictable phenomenon, and if other galaxies could follow the same path. Then there's the European Space Agency's Euclid mission, already scanning the cosmos for clues about dark matter's role in shaping galaxies. Early observations suggest the Phoenix galaxy's dark matter halo is unusually lumpy, with dense knots that could act like gravitational anchors, trapping gas where it's needed most. Euclid's three-dimensional maps will test this theory, revealing whether dark matter is truly the invisible hand guiding the galaxy's resurrection. If so, it could mean dark matter isn't just a passive scaffold, it's an active player in cosmic evolution, capable of steering entire galaxies toward immortality. But the real game changer, the upcoming Lynx X-ray Observatory, currently in development. While Chandra gave us glimpses of Phoenix's black hole eruptions, Lynx will watch them in real time, with resolution sharp enough to see how shockwaves from the black hole's jets compress nearby gas clouds. Does this compression trigger star birth or stifle it? Lynx could settle the debate once and for all. And if it catches a star mid-rebirth, perhaps a red giant shrinking back into a younger state, it would be the smoking gun proving that stellar immortality isn't just possible, but happening right now in the cosmic wild. These missions aren't just about solving Phoenix's riddles, they're about redefining what we thought was possible. If the galaxy's rebirth has a universal blueprint, we might discover entire populations of immortal stars hidden in the cosmos. Or we could learn that Phoenix is a cosmic outlier, a freak of nature with conditions too rare to replicate. Either way, the answers are coming, and with them, a new chapter in our understanding of life, death, and the strange worlds that refuse to choose between them. Long before telescopes pierced the heavens, humanity told stories of firebirds rising from ashes, creatures like the Egyptian Bennu, the Chinese Feng Huang, and the Greek Phoenix, all symbols of cyclical rebirth. It's almost eerie how these ancient myths echo the Phoenix galaxy's defiance of cosmic death. Could our ancestors have glimpsed something profound about the universe's rhythms, even without the tools to prove it? Take the Egyptian Bennu, a heron-like bird said to erupt into flames every 500 years, only to emerge renewed from its own pyre. The parallels are striking. Just as the Bennu's combustion precedes its revival, the Phoenix galaxy's violent supernova seemed to fertilize new stellar birth. Then there's the Persian simurgh, an immortal bird nesting in the tree of life, whose feathers heal the land. A poetic mirror to how the galaxy's dying stars scatter heavy elements that nurture future generations. Even the Hindu Garuda, a celestial raptor born from a blazing egg, carries echoes of stars igniting within supernova remnants. What's uncanny isn't just the shared imagery, it's the timing. Many of these myths emerged during eras when civilizations first mapped the stars, like Babylon's astronomers tracking planetary motions or the Maya charting Venus cycles. Could repeated observations of cosmic events, supernova lighting up the night sky, comets blazing like fiery birds have seeded these legends? The Crab Nebula's explosion in 1054, visible even in daylight, was recorded by Chinese astronomers as a guest star, while Native American petroglyphs may depict earlier stellar explosions. If a dying star's brilliance could inspire myths across continents, is it so far-fetched that the concept of rebirth resonated deeply enough to predict a galaxy's behavior millennia later? Yet there's a tantalizing alternative. What if these myths weren't just metaphors but fragmented memories? Some theorists propose that advanced ancient cultures, now lost to time, might have possessed knowledge of celestial cycles through meticulous observation. The Dogon people of Mali, for instance, famously knew of Sirius B, a white dwarf invisible to the naked eye centuries before telescopes confirmed it. Could other civilizations have decoded patterns in stellar deaths and rebirths, encoding them in myth as cautionary tales or cosmic blueprints? Of course, correlation isn't causation. the Phoenix Galaxy's rebirth is physics, not mysticism governed by gravity and dark matter, not divine intervention. But the persistence of these stories across cultures hints at something universal: humanity's longing to believe that destruction isn't final, that even the cosmos has a way of beginning again. Whether by accident or intuition, our ancestors may have glimpsed a truth modern science is only now uncovering, that in the darkest corners of space, death is just another kind of spark. What if the Phoenix Galaxy's immortal stars aren't just bending the rules, they're hacking reality itself? Enter quantum immortality, a mind-bending theory so radical it straddles the line between astrophysics and science fiction. At the subatomic level, particles don't behave like tiny billiard balls, they exist as probabilities, flickering between states until observed. Quantum fluctuations can spontaneously create particles from empty space or tunnel through barriers they shouldn't bypass. Now stretch that weirdness to cosmic scales. Could stars in the Phoenix Galaxy be exploiting quantum mechanics to reset their aging processes, like cosmic computers rebooting their own code? The idea isn't entirely without precedent. In labs on Earth, quantum systems occasionally jump to lower energy states without obvious cause, a phenomenon called quantum tunneling. Apply that to a star's core, where fusion reactions are fundamentally quantum events. Under unimaginable pressures, protons overcome their mutual repulsion not through brute force but by tunneling through it. Normally, this process follows predictable rates, but in the Phoenix Galaxy's extreme environment, with its crushing gravity, turbulent magnetic fields, and constant stellar collisions, quantum effects might amplify unpredictably. Imagine a dying star's core on the verge of collapse, suddenly tunneling into a more stable configuration. It wouldn't be rebirth, it'd be a quantum rollback, like hitting undo on stellar death. Some theorists take this further. The many worlds interpretation of quantum mechanics suggests every possible outcome spawns a new universe. In most realities, stars die predictably. But in rare branches of the cosmic tree, quantum fluctuations might nudge a star toward survival. If the Phoenix Galaxy's unique conditions somehow select for these unlikely quantum pathways, we could be observing a pocket of reality where stellar immortality isn't just possible, it's inevitable. Picture a cosmic casino where dying stars keep rolling quantum dice until they land on survival, while the rest of the universe sees only the losing throws. Of course, this is speculative territory. Mainstream astrophysics favors explanations involving dark matter dynamics or black hole feedback over quantum resets. But consider this: the Phoenix Galaxy's most baffling stars often sit near its supermassive black hole, where space-time warps into a pretzel. In such extreme gravity, quantum effects normally confined to microscopic scales might bubble up into the macroscopic world. It's not unlike how Hawking radiation, a quantum phenomenon at black hole horizons, defies classical physics. Could similar weirdness be propping up stars that should have died eons ago? For now, quantum immortality remains a tantalizing what if. But as telescopes probe deeper into the Phoenix Galaxy's heart, they might catch signatures betraying quantum trickery, perhaps stars flickering between energy states or emitting particle patterns that defy fusion models. Until then, this galaxy keeps its secrets close, whispering a reminder that the universe's rulebook might have pages we haven't even glimpsed yet. Picture a defibrillator's electric jolt reviving a dying heart, now scale that up to galactic proportions. That's the bizarre role the Phoenix Galaxy's black hole jets might play, blasting dormant gas clouds with enough energy to shock them back into star-forming life. These jets aren't just random outbursts, they're precision strikes carving through space at nearly the speed of light and colliding with frigid gas clouds like cosmic paddles, delivering a life-saving charge. When a black hole feeds, it doesn't just swallow matter quietly. As gas spirals toward oblivion, magnetic fields twist into colossal funnels, launching twin jets of charged particles that scream across the galaxy. Normally, these jets are agents of destruction, sterilizing everything in their path. But in the Phoenix galaxy, something flips the script. Instead of obliterating gas clouds, the jet's shockwaves compress them, squeezing the gas until it collapses under its own weight, triggering stellar birth in the least likely places. It's as if a wildfire's heat could coax dormant seeds to sprout mid-inferno. Hubble's images reveal the aftermath, glowing filaments of gas, lit up like neon signs along the jet's paths, each one a stellar nursery forged from chaos. Some of these filaments are so dense, they've already birthed star clusters younger than human civilization. The secret lies in the jet structure. Unlike the ragged, diffuse winds from supernova, black hole jets are tightly focused, like laser scalpels slicing through the galaxy. When these narrow beams punch into a gas cloud, they don't just heat it, they create shock fronts that ripple through the cloud's interior, triggering cascades of collapse. Here's where the metaphor twists. A medical defibrillator works by resetting the heart's erratic rhythm. The black hole's jets do something eerily similar. In regions where gas is too turbulent to form stars, where collisions between molecules scatter energy wildly, the jet's shockwaves impose order. They synchronize the chaos, slowing particles just enough for gravity to take over. It's like a conductor silencing a cacophonous orchestra with a single downbeat, allowing the music to reorganize into harmony. But there's a catch. This cosmic defibrillation only works under perfect conditions. Too weak a jet and the gas shrugs it off, too strong and the cloud evaporates entirely. The Phoenix galaxy's black hole seems to have found the Goldilocks zone, its eruptions fine-tuned by the galaxy's unique gravity and gas distribution. Even the angle matters. Jets striking gas clouds head-on can shred them, while oblique hits create spiral density waves that nurture star formation. The implications are staggering. If black holes can jumpstart star birth this way, it rewrites the rules of galactic evolution. Suddenly, these destructive behemoths aren't just grim reapers, they're midwives, presiding over stellar rebirths in the unlikeliest places. And if the Phoenix galaxy's jets are the universe's first defibrillators, who's to say others aren't hiding in the cosmos, quietly shocking dead zones back to life? Astrophysics textbooks have long painted the life cycle of galaxies with confident strokes: birth, growth, dormancy, death. It's a tidy narrative backed by decades of observations and simulations, a framework so reliable that scientists could predict how galaxies evolve with startling precision. Then came the Phoenix galaxy, and suddenly the models fell apart. Supercomputer simulations designed to replicate galactic behavior down to the last supernova couldn't explain how a galaxy this massive could reignite star formation after its black hole should have sterilized it. The equations said it was impossible. The universe, it seems, didn't get the memo. Take the quenching problem, the long-standing puzzle of why massive galaxies run out of star-forming gas. For years, astronomers assumed supermassive black holes were the culprits, their outbursts heating gas to millions of degrees until it became too diffused to collapse into stars. Models predicted that once a galaxy like Phoenix reached a certain mass, its black hole would inevitably shut down star birth for good. Yet here's Phoenix defying the odds, turning its core into a stellar nursery despite the black hole's rage. It's like watching a fire reignite in the middle of a hurricane. The discrepancy forced scientists back to the drawing board, questioning whether they'd misunderstood black hole feedback entirely. Even dark matter models took a hit. Cosmological simulations assume dark matter halos act like static scaffolds, their gravity shaping galaxies but not directly influencing their gas dynamics. But Phoenix's halo appears to be anything but passive. Its gravity seems to actively funnel gas back into the galaxy's core, like a cosmic plumber fixing leaks faster than they can drain. When researchers plugged these observations into existing simulations, the results were chaos galaxies either collapsed too soon or burned out too fast. The Phoenix Galaxy's behavior demanded a new variable, dark matter that doesn't just sit there, but plays an active role in recycling galactic fuel. Then there's the star formation crisis. In most galaxies, the rate of stellar birth follows a neat relationship tied to gas density. Phoenix laughs in the face of this rule. Its star formation isn't just efficient, it's reckless, churning out hundreds of stars annually where models expected single digits. Some regions show stars forming in densities so high, they violate long-standing thresholds for gravitational collapse. Imagine throwing a handful of sand into the air and watching it arrange itself into glass sculptures mid-fall. That's the level of defiance we're dealing with. What's thrilling isn't just that the models failed, it's how they failed. Phoenix didn't nudge predictions slightly off course, it sent them careening into uncharted territory. For astrophysicists, that's not a setback, it's an invitation. Every discrepancy is a clue, a signpost pointing toward deeper truths hidden in the math. The galaxy's rebellions have already inspired new theories. Dark matter that interacts with itself, black hole jets that fine-tune star formation, quantum effects scaling up to galactic proportions. Textbooks are being rewritten in real time, not with erasers but with particle detectors and space telescopes. This is the beautiful irony of science. The moment we think we've figured something out, the universe throws a curveball and suddenly, the questions outnumber the answers again. The Phoenix Galaxy isn't just a cosmic oddity, it's a reminder that the universe's greatest gift is its refusal to be predictable. Every failed model isn't a dead end, it's a door cracking open, revealing another layer of the cosmos's endless creativity. Some stars in the Phoenix Galaxy don't just defy death, they seem to predate existence itself. Astronomers studying this cosmic oddity have stumbled upon a paradox. Certain stars exhibit chemical compositions and cooling rates suggesting ages older than the 13.8 billion years our universe has existed. At first glance, it's as if these stellar ancients were here before the Big Bang, a revelation that would upend everything we know about cosmic chronology. But before we rewrite physics, let's untangle this cosmic knot. One explanation lies in the way we measure stellar ages. Traditionally, astronomers estimate a star's lifespan by analyzing its metallicity, the abundance of elements heavier than hydrogen and helium. Older stars born before generations of supernova enriched the cosmos with metals tend to be metal-poor. Yet Phoenix hosts stars with baffling profiles. Some are metal-rich but display characteristics of extreme age, like cooled cores and dim luminosities that typically take longer than the universe's lifespan to develop. How the answer might involve the galaxy's relentless recycling. Stars here aren't just born from pristine gas, they're forged from the remnants of countless predecessors, inheriting metals from earlier generations at an accelerated rate. This rapid reprocessing could create stars that look ancient because they're built from ancient parts, like a vintage car assembled entirely from salvaged relics. Then there's relativity's slippery grip on time. Near the galaxy's supermassive black hole, gravitational time dilation could stretch stellar lifespans from our perspective. A star orbiting close enough might age only a few billion years locally while appearing far older to distant observers, like a clock ticking slower in a high-gravity funhouse. Combine that with the galaxy's chaotic environment, where collisions and mergers constantly reset stellar conditions, and you've got a recipe for stars that seem to cheat not just death but time's starting point. But the most plausible culprit, observational ambiguity. Determining a star's age isn't like reading a birth certificate. It's detective work with cosmic margins of error. Dust clouds in Phoenix could be skewing light spectra, making stars appear cooler, and thus older than they are. Or perhaps unusual nuclear processes in these stars' cores, fueled by the galaxy's extreme physics, mimic the signatures of advanced age. Even the universe's expansion plays tricks. Light from Phoenix has traveled nearly 6 billion years to reach us, meaning we're seeing it mid-evolution, not as it exists today. What looks like an antique might just be a snapshot of a star caught in a peculiar phase. The truth is likely a mix of all three, a reminder that the universe loves complexity more than tidy answers. These stars aren't truly older than existence. They're cosmic illusions, their stories distorted by time, chemistry, and our own imperfect tools. Yet their very strangeness pushes us to refine our models, to question assumptions, and to remember that in a place like the Phoenix Galaxy, even the laws of physics have room for reinterpretation. If stars in the Phoenix Galaxy can cheat death, could humanity one day steal their secrets? Picture this. A future where our power grids don't rely on dwindling resources but tap into self-renewing fusion reactors modeled after these celestial anomalies. Just as Phoenix's stars recycle their own remnants into fresh fuel, our reactors might mimic that process, harnessing the energy of dying plasma to ignite new reactions without wasting a single particle. Scientists are already exploring aneutronic fusion, a cleaner form of nuclear energy where reactions produce virtually no radioactive waste. Now imagine combining that with the Phoenix's relentless recycling, machines that don't just generate power but actively recover and reuse their byproducts, creating an endless loop of clean energy. The parallels don't stop there. Consider anti-aging research, where scientists study telomeres, the protective caps on our DNA that fray over time like a candle burning down. But in the Phoenix Galaxy, stars seem to lengthen their wicks, reversing decay by siphoning fresh material. What if we could borrow that strategy? Lab experiments with Yamanaka factors have already shown it's possible to reprogram adult cells back to youthful states, effectively resetting their biological clocks. Pair that with advances in nanotech that scavenge cellular debris like the way Phoenix's gravity hoards stellar ash, and suddenly, human cells might gain the ability to self-renew indefinitely, patching damage before it accumulates. Even space travel could be transformed. The Phoenix Galaxy's dark matter halo acts as a cosmic net, catching stray gas and pulling it back into the fold. Apply that principle to spacecraft propulsion, and you've got a system that harvests interstellar hydrogen on the fly, converting it into fuel mid-journey. No more lugging heavy tanks, just an engine that feeds off the universe itself, much like Phoenix's stars repurpose their surroundings. NASA concept of busted ramjets already toys with this idea, but Phoenix's natural efficiency could refine it, turning science fiction into viable engineering. Of course, there's a catch. The Phoenix Galaxy's tricks depend on extreme conditions we can't easily replicate: supermassive black holes, quantum-scale phenomena, gravitational forces that warp spacetime itself. Yet history shows us that nature's wildest blueprints often inspire breakthroughs. Velcro-copied burrs, sonar-mimicked bats. Who's to say we won't crack stellar immortality's code next? The universe has handed us a workshop manual written in starfire. All we have to do is translate it. What if the Phoenix Galaxy's immortal stars aren't natural at all? Before you dismiss this as sci-fi speculation, consider the Fermi paradox, the eerie silence of the universe despite its apparent readiness for life. If intelligent civilizations exist, why haven't we seen them? One unsettling answer: maybe we have. The bizarre behavior of Phoenix's stars, their unnatural longevity, their chemical oddities, their defiance of cosmic decay raises a wild but tantalizing question. Could these objects be megastructures built by civilizations so advanced they've mastered stellar engineering? Take Dyson spheres, hypothetical constructs where aliens encase entire stars to harvest their energy. A star wrapped in such a shell might emit unusual infrared signatures, its light dimmed but its heat bleeding into space. Some stars in the Phoenix Galaxy show exactly that: unexplained dips in visible light paired with excess infrared radiation. Normally, astronomers attribute this to dust clouds or debris disks. But what if it's not dust? What if it's architecture on a scale we can barely fathom? A celestial power grid built by beings who have turned their suns into batteries. Then there's the timing. Many of Phoenix's reborn stars flicker back to life with suspicious regularity, as if something or someone is fine-tuning their cycles. In nature, stellar processes are messy, unpredictable. Yet here, rebirths often follow patterns that mirror theoretical models of controlled stellar rejuvenation. Imagine a civilization that's cracked the code of star lifting, siphoning off a star's outer layers to extend its lifespan. The Phoenix Galaxy's helium-rich stars could be the result of such cosmic gardening, their fuel reserves artificially topped up like a carefully tended oil lamp. Of course, scientists are skeptical, and for good reason. The first rule of extraterrestrial hunting is to exhaust every natural explanation before invoking aliens. In Phoenix's case, the sheer energy required to manipulate stars dwarfs anything even a Kardashev Type 3 civilization could muster. The galaxy's black hole feedback loops and dark matter dynamics offer plausible, if exotic, alternatives to intelligent design. Besides, if these were megastructures, where's the waste heat? Dyson spheres would leak detectable energy signatures, and so far, nothing in Phoenix's spectra screams artificial. Yet the possibility lingers, not as a claim but as a challenge. The universe is stranger than we imagine, and the line between natural and engineered may blur in ways we're not equipped to see. For now, the Phoenix Galaxy stars remain cosmic mysteries, but whether they're miracles of physics or monuments to alien ingenuity, one thing's certain: they're forcing us to question what's possible in this vast, silent universe. The Phoenix Galaxy doesn't just challenge our understanding of stellar life cycles, it forces us to confront a far bigger question. Is this cosmic resurrection a freak accident, a one-in-a-trillion fluke of physics, or could it be a glimpse of something deeper, a hidden rulebook the universe occasionally follows when we're not looking? The answer might rewrite not just how we see galaxies, but whether the cosmos itself is wired for rebirth. On one side of the debate are the accident theorists. They argue that Phoenix's immortality is a perfect storm of extreme conditions. A supermassive black hole with oddly precise jets, a dark matter halo with freakish density, and a history of galactic mergers that stack the deck just right. After all, we've spotted thousands of galaxies, and only Phoenix behaves this way. Statistically, that suggests a cosmic roll of the dice, like a tornado assembling a functioning watch from scrap metal. Even the galaxy's location seems suspicious. It sits in a relatively quiet corner of the universe, free from the gravitational bullying of nearby galaxy clusters, as if isolation granted it the space to experiment with stellar resurrection. But the counterargument is tantalizing. What if we've been looking at the problem backward, instead of Phoenix being the exception? Maybe it's the only galaxy where conditions align to reveal a universal truth. Think of it like evolution on Earth. For centuries, biologists assumed life required sunlight until they discovered hydrothermal vents, where ecosystems thrive in total darkness. Those vents didn't break the rules, they exposed hidden ones. Similarly, Phoenix might be showcasing a mode of galactic rebirth that's always been possible but requires staggeringly precise triggers. This isn't just academic pondering. If stellar immortality isn't a fluke but a feature, it reshapes our search for life in the cosmos. Galaxies that renew themselves could sustain habitable zones far longer than the standard models predict. Imagine a civilization developing around a star that refuses to die, gifted with near-infinite time to evolve. It also casts Earth's position in the Milky Way in a new light. Our galaxy will eventually exhaust its star-forming gas, leaving future civilizations trapped in a slowly dimming sky. But if Phoenix's tricks can be decoded, could we one day engineer our own galactic rebirth, staving off cosmic entropy? The most mind-bending possibility, that Phoenix hints at a universe fine-tuned for renewal. Some physicists speculate that dark energy, the mysterious force accelerating cosmic expansion, might not be constant. Could it fluctuate, creating pockets where gravity temporarily gains the upper hand, allowing galaxies to reset their clocks? Or maybe the laws of physics themselves are more flexible than we thought, bending under extreme conditions to favor persistence over decay. Either way, Phoenix stands as a beacon, forcing us to ask, is the universe a chaotic accident, or is there, buried in the math, a bias toward revival waiting to be uncovered? For now, the galaxy keeps its secrets, but with every telescope pointed its way, we're not just studying a celestial oddity, we're testing the boundaries of reality itself. Whether Phoenix is a miracle or a blueprint, one thing's certain: the universe is far stranger, far more inventive than we ever dared to dream. Imagine holding the universe's remote control, a button that could reshape galaxies, tweak black holes, even rewind stellar death. With the Phoenix Galaxy as our blueprint, humanity could one day wield that power. But here's the catch: just because we can intervene in cosmic evolution, does that mean we should? This isn't just science fiction, it's an ethical crossroads that forces us to weigh our curiosity against the sanctity of the cosmos. First, consider the conservationist argument. Galaxies like Phoenix evolved over billions of years through natural processes: gravity, dark matter, and sheer chance. Tampering with that delicate balance risks unintended consequences. Think of it like introducing invasive species to an ecosystem. A well-meaning tweak could trigger chain reactions we can't predict. For example, forcing a dormant galaxy to reignite star formation might destabilize its black hole, sending lethal jets of radiation hurtling through inhabited systems. And who gets to decide which galaxies deserve revival? The ethics here mirror debates over terraforming Mars. Do we have the right to impose our will on a cosmic scale, or are some realms better left untouched? Yet the scientific allure is undeniable. Unlocking Phoenix's secrets could revolutionize energy, medicine, even our understanding of time. Picture harnessing stellar rebirth to create fusion reactors that never exhaust their fuel, or using dark matter manipulation to slow aging in human cells. The galaxy's defiance of entropy might hold the key to surviving the universe's eventual heat death, a literal lifeline for civilizations billions of years from now. The catch: experimentation requires interference. You can't learn to restart a star without first letting one die. This tension isn't new. Humanity has always grappled with the ethics of exploration, from colonizing continents to splitting the atom. But galaxies aren't continents. They're shared inheritances spanning billions of light years and potentially hosting countless civilizations. What if our tinkering erases evidence of alien life or disrupts a process another culture deems sacred? The Outer Space Treaty of 1967 forbids claiming celestial bodies, but no law stops us from rearranging them. Without cosmic zoning laws, we risk becoming the universe's reckless renovators. Perhaps the answer lies in a middle path: observation without alteration. Instead of playing gods, we could treat galaxies like wilderness preserves, studying their cycles without disruption. Telescopes like James Webb and future neutrino detectors might reveal Phoenix's secrets passively, avoiding the hubris of hands-on experimentation. Or we could adopt a prime directive for cosmology, intervening only when a galaxy's natural death threatens life elsewhere. One thing's certain: the Phoenix Galaxy forces us to confront our role in the cosmos. Are we stewards, scientists, or something in between? The stars won't judge our choices, but if we're ever to wield their power, we'd better judge ourselves first. The Phoenix Galaxy doesn't just defy the rules of stellar life and death. It shatters our perception of what's possible in the cosmos. From stars that rewind their own aging to black holes that act as cosmic defibrillators, every discovery here feels like a challenge whispered by the universe: think bigger. This isn't just a galaxy, it's a living laboratory where the conventional cycles of creation and destruction twist into something stranger, something cyclical. And the most humbling lesson, we've barely scratched the surface. For centuries, humanity saw the universe as a predictable machine, governed by rigid laws. Stars burned out, galaxies faded, and entropy marched forward, end of story. But Phoenix laughs in the face of that inevitability. Its stars don't fade, they reset. Its black hole doesn't just destroy, it sculpts. Even its dark matter, once thought to be a passive spectator, seems to play an active role in recycling cosmic material. The message is clear: the universe isn't just a clock winding down. It's a canvas, and the brushstrokes we thought we understood might be far more dynamic than we ever imagined. What does this mean for us? For one, it redefines the search for life. If galaxies can sustain star formation far longer than we believed, the window for intelligent life to emerge might be wider than we thought. Planets orbiting these immortal stars could have billions of extra years to evolve, creating civilizations that outlast anything we've dreamed. It also forces us to reconsider our own fate. The Milky Way will eventually exhaust its star-forming gas, leaving future civilizations trapped under a darkening sky. But if we could decode Phoenix's secrets, if we could learn to reignite dying stars or harvest dark matter's gravitational net, we might one day cheat cosmic entropy itself. Yet beyond the science, Phoenix offers something deeper, a reminder that curiosity is our greatest tool. Every time we think we've mapped the universe's rules, a place like this emerges, daring us to question, to reimagine, to stay humble. The night sky isn't just a static backdrop. It's a living, breathing puzzle, and galaxies like Phoenix are the pieces that don't quite fit yet. So keep looking up. The universe is stranger than fiction, and the next revelation might be waiting just beyond the next beam of starlight. What will we uncover next? So what do you think is really happening in the Phoenix galaxy? Are its immortal stars flukes of physics, or is there something even stranger at play? Drop your wildest theories in the comments. Maybe your idea will spark the next big cosmic breakthrough. And hey, if this journey through the universe's most defiant galaxy left you as awestruck as it did us, don't forget to hit like and subscribe. Because guess what? We're just getting started. Up next, we're diving into another cosmic head-scratcher, a black hole that shouldn't exist, defying every law of physics we know. Trust us, you won't want to miss it. Until then, keep looking up. After all, the universe loves a good plot twist.